Come back to our lectures. So let me check how many of you already. Okay, we have 38 students already. All right. In our today's meeting, we are going to continue our last night discussions on the 1D bar approach for solving finite elements problems. So last night we have looked at the system of linear equation that we are going to solve, which is in the form of KQ equal to F. And we have roughly look at the type of the loading that may involve in our analysis later, which is we have three types of loading. The body force, we have the traction force, and also the point load. And then we have looked in general as well the type of support conditions or the boundary conditions that may involve in our analysis as well. We have learned how to discretize our geometry, which is from the physical geometry. Physical geometry ni maksudnya apa yang kita nampak depan mata tu lah kan. Dia punya structures as we can have in our real problems. But somehow for finite elements modeling in finite elements, we have to chops, we have to divide, we have to discretize our geometry into smaller elements. We call it finite element. And in this first finite elements topics, we considering that our structure will be discretized into bar element, bar elements. Bar element of a uniform cross-section area. And then from there, we have looked at from the system of linear equations, then we can obtain what we call it as the unknowns in our system of linear equation, which is the Q. As you can see on the screen right now, we have the system of linear equation, which is arranged in the form of KQ equal to F, which is Q is our unknown. The variables or the variables which is the displacement that we are going to calculate out of these finite elements. And from the knowns nodal displacement Q is the nodal displacement, which is the deformations of our structure, which is calculated at each nodal point. But in some cases, we may interested to determine what is happening in between the two nodal points. For example, somewhere there. Then this must be can be predicted by using the field displacement equation, which is, if we can remember, Ux equal to N1 Q1 plus N2 Q2. Which is this is N1 Q1 plus N2 Q2 actually involve some interpolations technique in order to solve this equation, where by assuming that the variation between the 2 points in terms of displacement, in terms of the stress and strain, they varies linearly from one point to another, which requires in the interpolations where n1 equal to 1 minus z over 2 and n2 equal to 1 plus z over 2. where the z is given by the equations as shown in our at the bottom of our slide. All right. From the knowns nodal displacement, from the knowns field displacement, we can use this information to obtain the normal strain, which is just the gradients of the displacement in one direction in this case. So we are looking for normal strains in x direction. So the strains mathematically can be represented by du over dx, or also can be written as a dq over dx, where q is the displacement at nodal point as we solve or predict from the system of linear equation. But as I mentioned earlier, we have two coordinate system, which is the Cartesian in the x direction, and also we have the z, which is the natural coordinate system. To simplify the process, if we are working in the natural coordinate system, is much more easier. So by using change rule, we can rewrite the normal strain, which is initially we write it in the Cartesian coordinate system into the natural coordinate system by du over dz multiplied by dz over dx, which is this is actually equivalent to du over dx. And we know that, okay, we have like two parts here, du over dz and dz over dx. So kita ada dua bahagian di situ. So I use different colors to differentiate it. All right. Now we have du over dz. Okay, we have du over dz, where u is the field displacement, and the differentiation of field displacement du over dz can be obtained from this relation. Okay, kita patah balik kepada field displacement ni, kita ada u, and then dalam u ni kita ada the term z, which is z ni dia ada dalam n1 and also n2. And then dz over dx. Then we know that we can relate the natural coordinate system to the Cartesian coordinate system by this equation. This equation here. So if we take dz over dx from this relation, then we obtain this expression there. And then if we take the field displacement equation, which is if we rewrite it by substituting n1 and n2 into this equation, then kita ada equation ini. So from there, to differentiate the du by dz, I recommend you to explain this equation first. Otherwise, it's a bit hard to differentiate it. Explain it first, then you will get something like u equal to q1 over 2 minus dz q1 over 2 plus q2 over 2 plus z q2 over 2. So apa yang kita nak buat kat sini, kita nak dapatkan du over dz, right? So if we differentiate du over dz, then we only get q1 over 2 negative plus q2 over 2. So if we further simplify this, then we can write our equation for du over dz ini, which is equivalent to negative q1 plus q2, which is similar to what we have in the equations represented just slightly above our solutions. So now we have du over dz and dz over dx. Then we multiply each other, similar to what we have in the normal strains equation. So, okay, from there, just now we have epsilon equal to du over dx equal to du over dz multiplied by dz over dx, and then this is equivalent to what we have here, where this equation we can further simplify this it's a mathematical expression here by taking b multiplied by vectors column vector of q1 and q2, where b here refers to these components. So b equal to 1 minus length of our elements multiplied by negative 1 and 1, and then our e here will be, if I take the strain will be 1 over le negative 1 1, and then multiplied by q1 and q2. So this q1 and q2 must be first calculated from the system of linear equation. Otherwise, we cannot calculate the normal strain. So in terms of the equation, you do not need to worry about the equation. Usually we will supply all the related equation. But in some cases, when you are asked to derive the equation, then you have to understand the concept of the finite element itself from the very first principle of the finite element itself. Tapi kalau you all boleh faham apa yang saya dah explain daripada awal malam tadi, then it will be very easy lah for you to do the derivation. Kita tak tanya derivation pelik-pelik pun. Whatever you have in the slide, usually we try to test you again whether you understand it or not. Then once we obtain the Q, we obtain the displacement. From the displacement, we can obtain the normal strain. And then from the normal strain, if we include the information from the material properties, which is the modulus of elasticity, to the normal strain equation, then this actually will give you the normal stress in our elements. Senang je kan? First kita kena tentukan, kena dapatkan Q ni dulu. Displacement, and then daripada displacement menggunakan kaedah yang kita buat sebentar tadi, which is this is just a du over dz, dz over dx. Kita boleh dapat normal strain, and then from this our solution, kita multiplykan dia dengan apa tu, kita masukkan information material, then kita boleh dapatkan normal stress. So if you look at these equations, the normal stress is actually kita dah tahu tadi kan, we know that the normal strain equal to B multiplied by Q, which is equivalent to 1 over length of the element, length of the elements, then we multiply by -1 and 1, and then this is our B, and then kita ada Q1 and Q2. That's mean untuk dalam satu elemen tu, kalau let's say kita ada elemen untuk node 1 dengan node 2 tu, kita dah boleh tentukan dah berapa strain, normal strain dalam this element. Elemen nombor 1 sebagai contoh, so saya tulis normal strain untuk elemen nombor 1. And then if we include the material properties, which is the Young modulus of elasticity of our structure, then we multiply to the all of this information, then it will give us the normal stress in this element number 1. So very straightforward. Okay, untuk setakat ni ada soalan tak? Saya rasa mungkin boleh faham dia, ataupun kalau apa ni still very hard to understand, boleh refer dekat apa tu saya punya recorded video dekat YouTube. Link saya dah sertakan dalam you all punya e-learning. Alright. Okay, now we comes to the not the hardest part, tapi dia involve some mathematics lah dekat sini. So if we can remember, when we solve the finite elements, we have to rearrange our equation in the form of system of linear equation. KQ equal to F, and we know already out of this system of linear equation, yang kita nak tentukan adalah the displacement. This is the Q, which is referred to nodal, the displacement at each nodal point in our structures or in our system yang kita nak solve. We know that Q may came from the body force, it may came from the traction force, and also the point load. But what if K matrix ni apa benda ni K matrix ni? So as I mentioned to you earlier, the K matrix is the metric that store some informations of our structures in each elements. Sebagai contoh, let's say structure saya ada 3 elemen. So ada 3 elemen. This is the element number 1, element number 2, and also element number 3. So saya labelkan dia punya nodal point dia dengan color merah ni. Ini adalah dia punya nodal point. So for each elements will have its own K value, K1, K2, and K3. Kenapa? Sebab structure kita maybe came from different type of material. Sebagai contoh lah, kalau saya lukis macam gini kan, saya punya structure tu, and then So kita diskretizekan dia kepada 3 elemen. So yang atas ni adalah saya punya bar element. Let's say untuk yang section yang besar ni saya gunakan material yang berbeza, mungkin stainless steel. Ataupun kedua-duanya aluminium, tapi aluminium yang series yang lain kan. Okay, this is aluminium type 1, and then element number 3 ni merujuk kepada element type, different type lah, ataupun type yang number 2. So, alright, in the K elements, in the K matrix, it will store the geometrical informations of our structure. Tengok sini diameter dia ni, dia akan memberikan A yang berbeza dengan A1 mungkin sama dengan A2 sebab dia punya size yang sama, tapi dengan dengan elemen nombor 3 ni dia ada difference diameter kan, so dia akan ada different value of A. And then the length of the element itself, okay, kalau kita dividekan dia dengan equal spacing, so semua sama lah, tapi tak semestinya the length of our element ni sentiasa sama. Dia mungkin L1 mungkin berbeza dengan L2, mungkin berbeza dengan L3. So this is the geometrical information. And then it's also stored the material information, which is E, modulus of elasticity of the material itself. But how can we obtain the K? Macam mana kita nak dapatkan K tu? Okay, in our course, we just refer to one approach, which is one approach to obtain the element stiffness metric, which is based on the potential energy approach. So this is the approach that we use to come up with the K matrix. Tapi dia ada approach lain. Ini adalah salah satu approach untuk kita dapatkan K matrix. So the potential energy is given by pi. So this is the total potential energy, which is the sum of the internal strain energy given by U, and then the potential energy of the external force. So omega ni adalah potential energy from the external forces, and then U adalah internal strain energy. So if we expand this U and omega, then we can rewrite the potential energy as the second equation that we have in the slide, which is equation yang ni lah. So if we look closely in this equation, this is our internal strain energy, U. So ini adalah kita punya U, and then the other three dekat sini ni adalah kita punya omega. So this is our U, internal strain energy, and then the other three terms on the right hand side of the equation adalah kita punya potential energy from the external forces. So if you look closely in this internal strain energy, kita ada apa? Kita ada normal stress, kita ada normal strain, kita ada area, dan kita ada dx. Okay. Yang ni kita dah discuss tadi, normal strain, normal stress dengan area kan. And then in these three terms, then you can see that we have F, which is, this F is actually referred to the body force. And then kita ada T, which is referred to the traction force. And then kita ada PI, which is referred to the point load. So these three terms here actually refer to the external forces that may exist in our systems. So ni omega ni adalah merujuk kepada dia ada relation dengan external forces. But U, okay, it involve the strain and normal stress in our element. And then mathematics itself kita kena diskutaskan dia itu finite element as shown by the bottom by the equation at the bottom of our slide. Alright, saya tak akan tak akan go very detail in terms of the derivation, but to obtain K, we just work on the internal strain energy in order to obtain the K matrix. So starting from the internal strain energy, yang mana kita ada stress, kita ada strain, which is we know that the stress is given by this equation, strain is given by this equation. So kita substitutekan dia dalam equation internal strain energy. Then we rearrange the equation. So bila kita rearrange the equation, then you will get the equation which is will be written something like the one that is at the most bottoms of this slide, which is dekat sini lah, this equation. Bila kita rearrange the equation tadi tu, and there's a part of this equation from this internal strain energy, which is this one. So this part of this internal strain energy, which is actually refers to the K matrix or element, or we call it as the element stiffness matrix. So stiffness kan, how stiff of our element? Stiffness matrix. Metric stiffness apa, Rais? Kekuatan, stiff. The element stiffness tak apa, nanti you all cari nanti dalam bahasa Melayu dia. Okay, and then this element stiffness matrix, as I mentioned to you earlier, it stores the geometrical informations of our element and also the material that apply to that particular element. So AE over L, and it's multiplied by the square of 2 by 2 matrix. So dia ada explain dekat sini juga. Alright. Kat sini boleh ni boleh faham setakat ni. So nanti untuk kita punya system of linear equation will be developed based on this K. K, kita ada K, kita ada K tadi tu. The big K, which is contributed from this K. We have Q, and then we have F. So by now, actually you should be able to understand what is K, what is contained in the K, how we can obtain the K for our structural problems. Sebab K ni kalau untuk when we solve fluid problem, then the K will be different type of K. If we solve heat transfer problem, we still have K, but the expression for the K itself will be will be slightly different because it will store different informations lah. Dekat sini sebab kita nak solvekan structural problem, so dia akan store kita punya structures geometry A dengan L dan juga material of the structure kan. Kalau untuk when we solve the heat transfer, we may need to store the some the heat transfer information macam conductivity, maybe the geometry as well in the K element. So untuk bar problem, our K will be in the form of AE over L dengan square 2 by 2 matrix. Contains 1, -1, -1 and 1. So now we done with K. We understand Q. Now let's look at how can we deal with the forces tadi tu, external loads. All right. So element vectors, element force vector. As we discussed last night in our meeting, there are at least 3 types of external forces that may involve in our finite element analysis for 1D bar, which is in the type of body force, FB, traction force, which is the force that apply to on the surface of our structure, body force, which is the force that may came from the gravity accelerations and also from the weight of the body itself. And then we may have the point load, which is the external load that apply to a specific point within our structure. So mana tadi saya dah explain yang pasal badan tu kan, badan, let's say badan kita macam gini, each section of our body carry its own body force. So dekat tangan ni, dekat dia punya center of gravity dia, so dia ada weight dia untuk tangan dia ni. Untuk tangan yang sebelah kiri ni, dekat center of gravity dia, dia ada weight dia sendiri. Dekat legs of our legs pun dia ada. Kepala kita pun dia ada weight dia sendiri. So similar to the structure as well. So to the let's say we have bar structure something like this. Ataupun kita tunjukkan dia dalam let's say I have a structure which is spanning in this direction. Sebab kita nak tunjuk effect of the body weight tu kan. So each of the structure at each center of gravity, so it contain its own weight. Let's say this is kita punya element number 1. So kita ada W untuk element number 1. So let's say this is our element number 2. So the element number 2 itself, dia ada berat dia sendiri. Okay. As we from these two examples, let's say saya ambil yang tangan je dulu. Ambil tangan ni saya pusingkan sikit. Ni tangan saya ni. Okay, tangan dia ni. So I bring it down here. So saya pusing lah dia senang sikit. Saya pusing, saya redraw. So that my hand will be in this position. Okay, and then it contains its own weight, which is in the gravity direction. Tapi this weight apply at the center of gravity, at the CG. Okay, in finite elements, we cannot solve this the body weight as it apply at the center of gravity. But somehow we have to transfer it into what we call the equivalence nodal of force that apply at each nodal point. Maksud dia, when we measure the weight of any object, actually that weight is actually refers to the weights that apply at the center of gravity. Tapi untuk for the finite element purposes, we have somehow converts from the center of gravity, the weight that is measured at the center of gravity, into the equivalent force that applied at nodes number 1 sebagai contoh, and also nodes number 2. So mathematically you all boleh tengok dekat slide ni lah nanti. Tapi physically I try to explain it physically how it works. Then if you work out with the mathematics, then you will find out that the way of we converting the force from the center of gravity into the equivalence node of force applied at node 1 and node number 2 can be represented by this equation here. Dalam slide ni. Daripada center of gravity tu, kita kena convertkan dia kepada equivalent nodal force. So kalau kita tengok kat sini apa yang berlaku, let's say weight, kita ada weight dekat sini kan, weight of our structures. And then of force weight multiplied by the gravity, we get the force. And then what happened here, sebab kita nak bahagikan dia sama rata kepada node nombor 1 dengan node nombor 2, so kita bahagikan dia kepada 2 je. Sebab kita ada 2 nodes kan. Kalau kita ada 3 nodes, kita kena bagi kepada 3 lah supaya dia sama rata. And then the body force we divide it by 2 because we only have 2 nodes. And then we multiply by vector 1 and 1, which is refers to F B over 2 ni, 1 apply to nodes number 1 and the other portions or the other half of the force due to the body force we transfer to the nodes number 2. So maksud dia, let's say saya ada berapa Newton dekat sini, let's say 2 Newton. Okay, 2 kilonewton ataupun 2 Newton, let's say lah 2 kilonewton apply at the CG, but we have to transfer it into the equivalence under the force, which is FB tadi kita bahagikan dia dengan 2 and then multiply by A and L, which is the geometrical information of our structure, and then kita transfer dia kepada node 1 separuh dengan kepada node nombor 2 sebahagian separuh lagi. Is it clear? Do you have any questions on this part? How we should deal with the external forces? So yes.
Yang ni derivation atas itu tak perlu tahu Asyik.
Kadang-kadang kita tanya tu just to test your understanding. Tapi mathematically ini yang berlaku secara matematiknya, tetapi physically kalau kita nak explain kepada orang, kita tak boleh nak explain matematik dia macam gini. So secara fizikalnya apa yang berlaku, which is just like apa yang saya explain sebentar tadi lah. Okay, mathematics dia macam gini, tapi apa yang matematik tu explain adalah secara fiziknya the load due to the weight and gravity acceleration yang berlaku dekat center of gravity. Okay, kita bahagikan dia sama rata, then kita letakkan dia kepada nodal point. Okay, instead of kita solvekan dia dekat center of gravity, kita solvekan dia, kita transferkan dia kepada nodes ni. Sebab finite element dia bekerja pada nodal point. Dia tak bekerja pada center of gravity in the first place. Tapi mathematics dia macam ginilah mathematics dia. Saya tak nak sentuh mathematics supaya nanti you all boleh go through yourself lah. Starting from the very basic stage dia, yang slide yang sebelah sini ni. Okay, daripada sini ni, daripada this equation, it goes there, and then kita ada U, kita ada F. U adalah yang ni, kan? Then you go step by step lah nanti. Tapi kalau kita tahu matematik, kadang-kadang nak explain apa matematik ni bagi tahu, kan? Itu pun satu benda juga. Macam orang cakap lah, 2 kali 5, 5 kali 2, sama tak? Saya tanya kamu ni, 2 kali 5, 5 kali 2 sama tak?
Sama.
Sama tak?
Jawapan dia sama.
Jawapan dia sama kan? Tapi apa physically maksud dia? Secara fizikalnya, apa maksud dia? Ni kedua-duanya ni 10. Kalau kita nak dapatkan 10 lah, memang sama 10.
Ada 5 kali.
Tapi actually dia tak sama.
5 kali
Satunya ada 2. Okey, tapi dia ada 5 set. 2, 3, 4, 5. Dan lagi satu, kita ada 5. 5 benda tapi kita ada 2 set. Which is, these two are not equivalent. Dia tak sama meskipun the contents, let's say kita ada limau lah kan. Limau ni, kita ada 10 biji. Tapi the way we order it. Okay, yang ni kita ada 2 kolom, ada 5 rows. Yang ni kita ada 2 row, ada 5 kolom. So kalau kita view it in this way, 2 kali 5 dengan 5 kali 2 ni tak sama, benda yang berbeza. Tapi the total limau tu masih 10. Macam gitu. So especially when you are working in the nak susun sorting your items, kan? 5 kali 2 dengan 2 kali 5 tak sama sebenarnya. Meskipun the number of orange ke apple ke buah ke still 10, tapi arrangement dia tak sama. So this is what the difference between the mathematics, the number and the physical meaning of it. So itu yang kita nak kena faham. Engineers is not just come up with the numbers only, but to understand what is actually this numbers refers to, kan? Tapi tu some people 5 kali 2, 2 kali 5 sama je 10. Sebab dia nampak yang 10 tu. Tapi if you look into different perspective in term of the sorting of the information, benda tu slightly different lah, slightly different. Alright, Okay, that's why in this slide dekat sini dia tanya kamu ni, can you give physical interpretation of FE ni? Itu FE ni maksudnya FE yang ni bukan F yang ni. Ni. Ini yang saya explain sebentar tadi tu. Kalau kita ambil the mass which is initially at the center of gravity, then we subdivided into two portion. Okay, subdivided into two portion, and then we transfer it to each nodal point. But we have to consider as well the geometry of our elements lah, which is given by A dengan L. Kalau tak, kita tak tahu ni apa ni nak bagi tahu F ni apa. F ni ALF over 2 multiply by column vector of 1 and 1 je lah yang kita boleh explain, kan? Kalau kita tak faham dia punya physical dia. Alright, now let's look at the traction force. Saya cuba completekan yang ni sebab dah nak habis ni. Due to the traction force, which is usually came in the form of the shear stress, the friction stress, so this friction force on our structures. So yang ni pun sama. Let's look. So I hope that you can work on this mathematics yourself. And then if we go straight to the final equation for the force due to the traction force, which is given by this equation. Kalau saya ambil one structure, this is our structure, and then these structures are exposed to the external or surface force, which is maybe in terms of the shear force, which is given by T in our case. We call it as a traction force. So this traction force is acting on all surfaces of our structure, kan? Semua permukaan kita punya structure tu berlakunya shear force, which is kita punya traction force. Tapi macam mana kita nak guna this traction force in our finite elements, which is our finite element later on will be, our structure will be model something like this saja, kan? Node 1 and node 2 to represent this point and this point. So from this traction force pun sama. What we can do is from the total traction force we that are acting all over our structure, then we consider the length of our element from the left to the right, and then we kita bahagikan dia kepada dua, and then we transfer it to the one half portion to the nodes number 1, and then the other half we put on this nodes number 2. So that means here our traction force from the total separuhnya ada dekat nodes number 1, and the other half is now located at nodes number 2. So our force tadi tu, force vector dalam KQ equal to F tadi tu, KQ equal to F. So our F, let's say for one element, then we have force due to the body force, which is kita ada apa tadi, A LF over 2. And then untuk nodes number 1, then kita ada untuk nodes number 2 ni, kita ada another half lah, LF over 2. And then untuk due to the traction force, then we have TL over 2 multiplied by 1. Kita ada 1 lah kat sini. And then the other half, which is located for the nodes number 2. So we have something like that. Considering that we have only one elements lah. Ini in term of dia punya teori. Nanti kita tengok when we apply to the structural problem, how this all the forces works lah. Itu much more better to understand. Okay, tapi kita tak ada slide untuk point load. Why we don't have slide for the point load? Because point load is very straightforward. It's already applied to the nodal point straight away. That means kalau force 2 will be applied there. Sorry, will be applied there and there. Then we apply it straight away on the nodal point. So let's say saya panggil kat sini F1, F2. Kat sini pun kita straight away call it F2 of the same magnitude and F1 of the same magnitude F it apply on the physical geometry. So dekat sini kita just tambah je. F1 adalah kita punya F1. Kalau 10 Newton, 10 Newton kat sini pun 10 Newton lah. Sama juga dengan F2. So this is the total force that is contributed from the body force, from the traction force, and also from the point load. Sorry, saya tulis kat sini lah. Dia much more better in terms of dia punya representation dia. From the body force, from the traction force, and from the point load. Kalau dalam kita punya problem tak dinyatakan traction force involved, so kita tak perlu kira lah, tak perlu consider yang traction force ni. Kita just consider apa yang dinyatakan sahaja. Kalau semua involved, so all these three contribution from these three forces must be included in our F. Dalam F ni lah maksud saya. F ni dia sama dengan yang dekat atas ni. Ini adalah the total force due to the body force, traction force, and also the point loads. Alright, I think you may have class later at 11. I think I stop it here, my lectures here. But just to inform you that kita ada one complete solution untuk satu example dekat bawah ni. And the explanations is already discussed in quite detail in my recorded lecture in the YouTube. So saya harap you all in your free time tu nanti go and visit my lectures and then try to understand how we use finite element to solve this kind of problem. So nanti dalam next meeting kita tak akan bincang lagi yang ni, then we try to get another problem, then we try to solve that particular problems together lah. Sebab kat sini dah ada kat sini, so kita tak perlu nak discuss lagi. So we try to solve another problems. Okay, so hari ni tak ada attendance sebab saya punya account sebab UTM rasanya dia punya account ada yang kena hack baru ni. So apa tu dia punya password untuk, saya tak sure your password pun mungkin perlu reset kot juga. Semua student kena reset, semua lecturer rasa kena reset password untuk masuk ke utm.my tu. Dan saya belum reset lagi, so tak dapat bagi attendance untuk hari ni. Tapi tak apa, once I reset, I will share through the kita punya Telegram group, so you can scan your attendance untuk kita punya meeting hari ni. I think that's all for today. I'm sorry for taking I think 1 minutes already after 11. Thank you very much and hope to see you again next week. So next week nanti kita